Let's debrief on your investigation. So you're using the limit definition in order to find the derivative of y equals x squared here. And applying the limit definition, stuff cancels, and then we have y prime is equal to 2x. So we started with x squared, and we ended up with 2x for its derivative. All right, whenever we had to apply the limit definition of the derivative, we had to square out this binomial here, right? And when you square out something, well, that one's pretty easy. You've known that one since probably Algebra 1, where it's the first one squared plus 2 times the product of those two, and then the last one squared. But really what you're using is Pascal's triangle, as we'll see here in just a little bit. All right, so for x cubed, whenever we plug that into the limit definition for the derivative, again, using Pascal's rule, and on this one, it is a 1, 3, 3, 1 for our coefficients. And then our x cubes cancel each other out. Everything that's left over has h's. You can factor one of those h's out and cancel it with the h in the bottom. And then whenever we plug in 0 for our h's, we're just left with 3x squared. So the derivative of x to the third is 3x squared. Okay, let's look at x to the fourth. So you can see over here in the margin, I had to get 1, 4, 6, 4, 1, because most people don't remember that. They may remember the 1, 3, 3, 1. Okay, that's good. So we use that to expand out x plus h to the fourth power, blah, 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 cancel stuff, factor stuff, and whenever we take the limit, we get 4x to the third. So the derivative of x to the fourth is 4x to the third. Are you noticing some sort of pattern yet? Maybe you need to see another one. Here's x to the fifth. I had to find the fifth row on Pascal's triangle right there to expand this thing out. And you can see that after this point, if you don't get it, you don't have enough room to get it on your paper. Look at this. There's no more room to do x to the sixth. Come on, Sue. You got to get it here. So after we do our cancellation, everything that's left over has an h involved. Let's factor that thing out, cancel it with the one that's on the bottom. All of these things go to 0, and we have 5x to the fourth. So the derivative of y equals x to the fifth is 5x to the fourth. Let's write all of these down. Just kind of recapping here. We're trying to get this thing that's called the power rule. Yeah. So when we have y is equal to x to the first, its derivative is y is equal to 1. And then when we have y is equal to x squared, its derivative is 2x to the first. But we usually don't write that. Okay. Y is equal to x cubed. Its derivative is, oh, wait a minute. I didn't put my prime marks on here. 3x squared, y to the fourth, y to the fourth, how about y is equal to x to the fourth, its derivative, y prime is equal to 4x to the third, and then we did one more, y is equal to x to the fifth, and its derivative was 5x to the fourth. Let's do one more, but not with the, the limit definition. Let's just use inductive reasoning. Y to this x, y equals x to the sixth. Speak words. Thank you. Well, what do you think the pattern is? Well, we can see, and maybe you already started to feel this pattern out whenever you're taking the derivatives in the last couple of units, the last couple of lessons. But we can see that the power goes down by 1, right? The power decreases by 1 for the derivative. But where is the number out front coming from? So this 2, where did that 2 come from? And wasn't that the power? This 3, that was the power. The 4 here was the power. The 5 was the power. Okay, so then I would expect the derivative of x to the sixth to be 6x to the fifth power. Now, I said that it was actually the exponent that's right here, but look at the limit definition for each one of these things. This was 5x to the fourth. If I go all the way back to the beginning, do I see where that 5x to the fourth was? It was the second term after expanding that binomial out. Same thing here. We have 4x to the third. It was the second term after we expanded out that binomial. x to the third was exactly the same thing. It was the second term. I wondered, did it work also for x squared, which was 2x? Yes, it absolutely did. Okay, anyway, so let's generalize it. So to generalize it, we should have, wait, I need some like dot, 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 dot. There we go. Y is equal to x to the nth. What we're going to do is we're going to take that n exponent and we're going to leapfrog it right down. Y prime is equal to n x to the, and now when you play leapfrog and you leap over somebody to get in front of them, there's now one less person behind you than there used to be, or at least the person that you just jumped over. So the power here should be one less than it used to be. This is called the power rule for taking derivatives. Let me come back over here and maybe write this up a little bit more. All right, so here were all of the derivatives that we just found, and then here was the general form of that for x to the nth. And this is what I was talking about in terms of the last lesson, that you may have started to make some sort of connections between the fact that when you had something polynomial, its derivatives power, its degree was one less than it used to be. So when we had a quadratic, its derivative was linear. When we have a cubic, its derivative is a quadratic, and so on. But also, let's also make some more of these connections. Let's take a look at this derivative. Y prime is equal to 2x. Right here at the origin, then the derivative is equal to 0. If I look back at the original function, that's where the vertex point is. On the right side of the origin, my derivative values are all positive. That means on the original function, it should be going upwards. It's increasing at positive slopes. And then likewise, over here on the left side of the origin, your derivative is negative, indicating the original function should be going downwards. It's decreasing in those spots. Same thing works for the cubic function. So for the cubic function, its derivative, well, the derivative is never negative. It is equal to 0, and it's equal to 0 right here at this strange point. So in terms of, say, in Algebra 2 or in pre-cal, you know that sometimes whenever a function crosses the x-axis, sometimes it jags over a little bit, it flattens out. That's called a point of inflection. And the derivative there was equal to 0 in this case. But everywhere else, the derivative was positive, indicating the entire function here was always going upwards. It was always increasing. So in the next video, like what we've done so far is just inductive reasoning to come up with this power rule. In the next video, we're going to use some deductive reasoning to see if we can actually prove that the power function is n times x to the n minus 1.